let's start this second class. So you remember last week we discussed many types of phenomena in nature. We asked questions, the color of the sky, why
the Eiffel Tower. The Eiffel Tower.
Eiffel Tower, why the clouds can block actually the light, not completely diffuse light, all these things, color of gems, and it turns out that all these phenomena actually they share the same physics, the same physical origin, which is scattering of light. Okay, that's what they share between them, and that's what they want to address during this course in general, and especially today. So whenever light meets matter, and if the matter is not perfectly homogeneous, there are some scattering centers, okay, then the light is forced to re-radiate in other direction. This is scattering, okay? If we understand this process, we understand why our eyes actually are connected to very small things. Okay, when you look at clouds, you are looking at very small particles of water, and we are connected to that because of scattering, single scattering, multiple scattering of light. Okay, so in this course, we will learn the foundation actually of this theory of scattering. And the idea actually is to be more specific, more practical, to be able to describe theoretically the phenomenon, to be able to measure it, and to make prediction in such system, not only qualitatively but also quantitatively. So we can actually make prediction there, and we will be using the language of electromagnetism. Okay. So last time I didn't show you the outline of the complete course. I think now with the introduction we can do it. Okay. So we introduced last time the topic. Today we are going to talk about scattering of light by particles. And the idea, the first progression that we have here is to describe, starting actually from the particle itself. So it's like what we call the bottom-up approach. Okay, so you start from one particle, then you put two, then n. Okay, to try to describe a complex scattering system. Okay, we'll see that this method is limited. Okay, it assumes there are many assumptions behind that if we want to be able to develop a theory. Okay, but we can actually do a lot of things with that. And so this is the first approach where we will first describe the scattering. Here we will go into electromagnetism and describe the radiation of light. We will see that for particular cases of particles, actually you have exact solutions. So that's very convenient, okay, and we can do many things with that. But if we want to go to multiple scattering, then the story becomes much more complicated, and there are completely different approach, more like from up to the bottom. So it's more like the approach of radiative transfer theory, diffusion approximation, where mostly we ignore the wave nature of light. Okay, we consider light as particles, so that's another approach, another approximation that will allow us to describe multiple scattering. Okay, and then we will go to actually what we cannot be described by particles, but which is really by essence a wave effect, which is the speckle of light. Okay, and especially also what we discussed last time, what I tried to introduce you to this concept of localization, which is a very strong interference effect. Okay, so a strong, I mean, the nature of wave is very important to describe these different aspects here. And at the end of this course, we will go through several applications of this field and describe random lasers and very important topic, the topic of imaging through scattering medium. Okay, so that's the general outline of the course. So we'll go reverse. Okay, so today we will discuss the theory of light scattering by particles. I will introduce a number of concepts, not too many, so you will not be like overrun by that. But I want to introduce some formalism to be able to describe the physics here. This is actually extracted from this book from the Van der Hulst, light scattering by small particle. There is another book, here, the Kerker. The Kerker also is a well-famous book, but this one is really well explained. So if you are interested to go deeper, I encourage you to open this book. So what is the outline of the course today? So we will discuss this concept of scattering. You have an incident wave, you have a scattering medium, scattering object, okay, and we observe the scattered light on the other side of the system in other directions, okay. So this process here will be described first by introducing the scattering amplitude. So the scattering amplitude will tell us about how strongly the incident wave has been scattered by the object, okay, and in which preferential direction. So that's the scattering amplitude. Then I will explain what is the cross section. So the cross section is a measure of how much light has been lost in the scattering process. Okay, I don't go into the subtitles here. And we will address a more complex problem, which is the problem of considering polarized light, so vectorial field. Okay, and we know that light is polarized. Okay, that makes things a little more complicated, and we will describe how to handle this problem. Not going too much into details, but just to give you the direction in case one day you are facing this question. Okay, so let's start. Scattering amplitude. So the scattering amplitude is the probability amplitude of the outgoing wave relative to the incoming wave. So you have a wave coming onto the scatterer, and you want to know in different directions what is the probability to find energy, to find a wave on the other side. Okay, so I want first to introduce a number of assumptions to describe this physics here. The first one is elastic scattering. We discussed that last time, if you remember. So elastic scattering assumes that the incident wave and the scattered wave have the same wavelength. Okay, so there is no absorption by the atoms. There is no interaction with the vibration of molecules, for instance. That's the case for Raman scattering, which is an inelastic type of scattering. Okay, so we limit ourselves to elastic scattering. We will consider also absorption. That's possible also, but mainly we will focus on that. So that's the first condition, the first assumption. The second assumption, so wavelength is conserved. Okay. Second assumption is the fact that the scattering process is independent. So this is called the independent scattering approximation. So what is it about? The idea is that changing the position of the scatterer will not change the final result of your scattering. Okay, so in that case, you just ignore the phase relation between the different scattered waves. Okay, they just add up in intensity, not in field, not in phase. Okay, so when is this condition possible? If you have some suggestion, when can we assume that, let's say we have two particles, okay, light comes and it is scattered by the first one and the second one, okay, so I will have a pattern, a scattering pattern at distance from these two scatterers. If I move them around, okay, I would like to have no dependence, so an independent scattering picture relative to the position of these two scatterers. Okay. So typically, what you assume is that the particles are far enough away, so not to interact with each other. Okay. So that's the condition of independent scattering. in other words, the scattering can be described for one particle without accounting for the others. Okay, so in that case, particles must be far apart, at least. In that case, phases are randomized. Okay, and the addition of the fields is incoherent. Incoherent means we don't take into account the phase, the fields, but we just add intensities. Okay. So in other words, what we observe at the output is a sum of intensities, not fields. So the total intensity scattered is the sum of the intensity scattered by each scattering center. Okay?
The sum of it.
The sum of it. So sum of it. So this is called
in the same point.
Yeah, at some point you measure the intensity. Okay, this is the sum of the intensity scattered by each of the scatterers. Okay, so this is called an incoherent sum. Okay, you don't consider the interference effect between all the contributions. Okay. So it's a strong assumption here for sure. Okay. Most of the time, for instance, if you consider a cloud or fog, okay, all the particles are constantly moving. Okay. So in principle, this can be applied. I mean, there is a complete randomization of the phases, and you can add incoherently the intensities. So that's the second condition, the second assumption. And the third one, so this is called single scattering approximation. So you can understand what it means by its name, okay? It means that the light is scattered only once when it crosses the medium, okay? So what would be the case? In which condition we would have this type of condition here, single scattering. Light comes, it will meet one scatter and then escape from the system. What would you suggest? For here, the system has to be diluted, not dense, okay, that's one thing. Here, actually, you need to have a system which is thin, okay? If it's thin enough, okay, the system is almost transparent and the scattering is only single scattering approximation, okay? Remember in the Eiffel Tower, that was the first level of the Eiffel Tower where you can see the light directly, okay? But there is some scattering, you see some light around, also around the Eiffel Tower, okay? So typically, in that case, the condition is that the medium is optically thin, okay? We will define this condition, it means optically thin, but it means that there is no multiple scattering. The light encounters objects, scatters only once, okay? With all these approximations, with all these assumptions here, then we can use what I'm going to describe for one particle and actually generalize that to many particles, okay? And consider a medium with many particles, as long as they are far apart, so a dilute system, and the system is optically thin. Okay. Light, we see better here. Light scattered by n particles is n times the light scattered by one particle. Okay. So the total scattered light. Okay. Scattered light is the sum of each scattered light by each center. So if you remember this picture here, so how can we test for single scattering conditions, single scattering approximation? And that's what I wrote. If you double the density of the system, of the cloud, so you go from this floor to the next one, you double the density, for instance, then the intensity is doubled. Okay, so you just count once the scattering by one particle. So if you multiply their numbers by 2, double the number, then you double the intensity scattered. And the test for independent scattering, as I said before, if you move the particles around, we should see the same picture, okay? So there is no phase dependence, no phase relation between the scattering by different particles, okay? Any question? Is it clear now? Yes? So just keep in mind this condition, single scattering approximation and independent scattering assumption. So if we go a little bit more into the physics here, so if you consider a volume of the cloud, for instance, with those various particles there, okay? So as the wave propagates through the system, okay, after a distance L, part of the light will be scattered, will be lost, okay? And what goes through is the light that has not been yet scattered, okay? So you can write that the intensity, the transmitted intensity after a distance L is the incident intensity I0, and actually it's an exponential decay, okay? As light is lost in another direction, the intensity decays along this volume in the forward direction. So we are looking in the forward direction, the same direction as I0 here, and the exponential decrease like minus L over small l, and if you remember, this small l was defined as the mean free path. Okay, we gave last time a very rough definition. We said that the mean free path is the distance between two collisions. Okay, so this quantity L over small l defined as actually what we call the optical thickness. Okay, so what is called an optically thin sample will be a sample where the length of the system divided by the mean free path is small. Okay, let's say less than 0.1. In that case, you can assume that the scattering is only once. Okay.
So the particle, the photon of the light will scatter only once inside the cloud? Inside the cloud.
Inside the cloud, because the cloud is so it's given by L here. Actually, the thickness is thin enough, okay, or the ratio.
Sorry, what's the optical thickness?
So optical thickness is actually this ratio. You compare the length of the system.
Yeah, but what does it mean? Like L so describes what?
L is the physical length. L is the physical thickness of the medium. Okay. So if you have a 10-meter cloud, okay, that is a physical thickness, okay. To get the optical thickness, you divide actually by L, which describes the scattering, okay. So you don't want to scatter inside this volume too often, only once actually, okay. So this has to be small enough.
This is the condition for a single scattering, and also
why? Because just because L is the distance between two consecutive scattering, okay? So if small l is larger than big L, okay, that means that the small l is much larger. That means that you never encounter twice a scatter. I mean, the light is never twice scattered, okay? So that's a number. I mean, you can fix any number, but it has to be smaller than so the mean free path has to be smaller than L, okay?
Yes.
And then when
the exponent will be like equal to 1, and then I will get I equals to I0.
Almost, yes.
Yes.
Yeah, almost. Okay. Now, if you have a larger optical thickness, okay, this is still small, but then you have to start to put correction to introduce second scattering, third scattering. I mean, depending on this number. Okay, so we can have an expansion like that and describe the system. Okay, so I try to give you some feeling of this condition. Okay, it's not obvious. I mean, to see the difference between independent scattering and single scattering. Okay, that's with two different conditions. Okay. If I ask you which one is the more severe condition, which one gives the worst constraints?
Independent.
So you say so. I mean, if I have independent scattering, do I have automatically single scattering or not?
No. If you have single, so you have independent. Yes.
Yeah, right. Okay, so it seems to be clear. Okay, so as I told you in the introduction, let's start with a simple case, which is the case of scalar waves. Okay. What do I mean by scalar waves? This slide in the wrong way. Okay, so a simple example is the sound waves. Okay, sound waves in air. Okay, so this is typically scalar wave. So the scalar wave is described only by one number. Okay, that's the idea. Is to have only one number to describe the wave. So P is a scalar here. P is the pressure. Okay, and that's the only quantity that describes the sound wave. So that's to give an example. Okay. Quantum mechanics also, when you consider the wave function psi here. Okay, so this is also a number, not a vector. Okay, not yeah. Okay, and for us, we are interested in electromagnetic waves. So in general, electromagnetic waves, and they are related to Maxwell equation and all that. We know that they are vectorial. Okay, so how can we describe electromagnetic waves as scalar waves? That's a little bit stretched, right? But there are some cases actually. There are some cases. The main case, the well-known case, is the case of waveguide geometries. Okay, so we consider like an optical fiber, propagation inside an optical fiber. Actually, the equations are very similar to this equation. If you look in the transverse direction, that's another example actually. So this is a cavity, a microwave cavity with scatterers. Okay. And you remember the simulation, so that's exactly like in the simulation. You excite at one point, there is an antenna somewhere. By these holes, you can introduce an antenna. The wave propagates inside the system, okay? And you can see actually the time of the evolution as the same as the propagation along an optical fiber, okay? So distance in the optical fiber will be time here, okay? In that case, in this case of, this is like a slice of a waveguide, if you prefer. Okay. In that case, you can have TE modes or TN modes, and the equation can simplify actually into a scalar wave equation. Okay, so that's an interesting case where this is possible actually to have scalar waves for electromagnetic waves. Another one is, by the way, this other system, scattering system. Okay, why? Because even if the electromagnetic waves are polarized, okay, after many scattering, the polarization will be completely randomized, okay? So we can completely ignore this parameter, polarization, and we can describe the wave as a scalar wave, okay? So a scalar field is a function associated with a single number at any point in the space at any time. So the scalar model will actually treat the light intensity and the phase only, no vectorial description. Okay. Okay. Good. So scattering of scalar wave by a particle. Let's start to formalize that a little bit. Okay. So amplitude of the incident wave. So we describe the incident wave in a regular way. Okay, typically we use the phase term here, which introduces the space and the time here. The phase accumulated in position and in time. Okay, so this complex number here, exponential I k r minus I omega t. Okay. This is a real quantity, so we take the real part of it, okay? So this is the standard description of a field, of a scalar field in space. So that will be our incident wave, okay? So E0 is a scalar amplitude. E0 exponential IKR is what is called the time-independent complex amplitude. Okay, if you ignore the time term here, time dependence. K is the wave vector, K is omega over c, or 2p over lambda. C is the velocity of light. Actually, velocity of light in the medium surrounding the particle. Okay, that's very important, by the way. Always keep that in mind. Don't take C as the velocity of light standard. Okay, think about the medium, and if there is a matrix like a medium with index n, so you take C over n, not C. Okay. Okay, so let's describe the scattering process. So we have our incident wave, okay, coming onto the scatterer here, or the medium that scatters light, okay, which is represented by this function S of theta phi, okay, and we are looking in the far field, okay. So we take R to the infinity, okay. So imagine that, I mean, this distance is like very far, okay, and we look at the scattering amplitude here in a particular direction, theta and phi, okay, because there is also this yeah, here. So we can just consider a spherical system of coordinates, okay. So we have theta and phi. So we consider, I should have put it here. We consider here this plane, the plane of the board here is called the incident plane wave. The plane of incident, or the scattering plane. Okay, the plane of scattering plane. Okay, in this plane you can describe only one parameter, which is theta, but actually this is in all direction. Okay, so there is theta and phi, where phi is described as you can see here, as you know. So this function here, S of theta phi, is called the scattering amplitude, okay, and is given actually by this function here. So the scattering amplitude of the field is the incident scattering, the incident amplitude of the scattering of the field, the incident field, times this function here, times S here, S where U is theta phi, okay, so S is the scattering amplitude. So what is the meaning of this function? So if I just hide that, okay, what is this function here? What does it describe?
The change of the amplitude is function of R, basically. Like, you can see that the magnitude like decrease is function of R.
Right, and there is a phase term here, okay, which gives you the phase accumulated over the distance, okay. But you see that this function is completely isotropic.
Potential of scattering. I don't know how to describe it, but it reminds me the way we look at potential. Like
we see that will be for next week. We'll talk about that. But more simple than that, this is just a spherical wave. This is the description of a spherical wave, okay, with the phase accumulated in all directions, the same phase accumulated in all directions. So it's really a wavefront, a spherical wavefront that gets further and further away from the scattering center. And the R here is the normalization, okay. If you take the intensity, so the square of this expression, that will give you a 1 over R squared, okay. And what is the surface of the sphere? It's 4 pi R squared, right? So the R squared and the 1 over R squared will compensate, and you get a conservation of energy actually at any distance from the center of the sphere. Okay? So this is simply a spherical wave, okay, which goes away from the scattering center. So we are looking in the far field, okay, at large distance. We're not looking really at what happens really close to this object, okay. We are not interested in that. That can be very complicated, okay. But at the end, when you look in the far field, this is simply a spherical wave, okay, that go away from the center, okay. And this spherical waves is weighted by this function here that tells you that in particular direction theta and phi, okay, you have a given amplitude, okay? So it's a spherical wave, but with different amplitude in a different position in space, okay? So that's, and you see that S does not depend on R, okay, it depends only on the direction, okay? So as the S of u is the scattering amplitude, okay, this is a complex number in the direction u, which is in spherical coordinate theta phi. S of u depends on u, okay, it depends on the characteristic of the particle, okay, its shape, its size, its composition, and obviously it depends also on the frequency of the wave, the incident wave on the system, okay. So that's really very the basic, I mean, the starting point of the description of the scattered field in the far field. Okay, again, by introducing this function here, this scattering amplitude, which is simply multiply a spherical wave going away from the system. Okay. So the scattering amplitude is also called the far field scattering function. So that's a way to write it. You can write it slightly differently. This is just a matter of notation. So instead of S of u exponential I k r over r, okay, we can write it like that. Okay, we introduce this term here, k. So if you write it like that, this quantity is dimensionless, so S prime of u is also dimensionless. Okay, so it's just a convention of writing here. So this is called the normalized scattering amplitude, and it's nice because if you consider not the field, but the intensity, the scattered intensity, so the scattered intensity, which is the norm of the norm squared of the field, okay, will give you the modulus square of S prime over K2 R2 times the incident intensity I0.
Question.
Yes?
So what do you mean by dimensionless? Dimensionless.
There is no, because K is the inverse of distance, yes? It's 2 pi over lambda, so times R. There is no dimension here.
I see, yes.
Here there is no dimension,
Yeah,
okay?
yeah.
So S, and this is the same dimension, so S has no dimension.
Okay.
It's just
What's the difference between that ES and the
previous one,
Yeah.
the IK, the wave vector. The wave vector, you see. Okay?
But why? Yeah.
No, this is just for defining the S. Okay, you can put the K in the S or out of the S. It doesn't change anything.
So it's the same formulas, but
It's the same formula, just two different ways to write it. Okay? Okay? So we have seen the amplitude, scattering amplitude, the scattered intensity, important parameters. So we will see that what needs to be defined here is the ratio of the index of the scatterer compared to the environment. Okay, so if we are in free space, n0 is 1, and n1 is the scattering, the index of refraction of the scatterer. But you can be like in water and study the scattering by a bubble. Okay, so it will be reversed. So n1 will be like 1, and n0 will be the index of refraction of water. Okay, so you have to think about that. And to normalize everything, we can define a size parameter which compares the perimeter of the object, if it's, let's say if it is a sphere. So the size 2 pi, the typical size of the scatterer divided by lambda. Okay, so K times A. Remember that when this number is close to 1, we know that we are going to experience very strong scattering. Okay, because we are on the same order in wavelength as the size of the object. Okay, So that will introduce, that will create strong scattering.
M and M are the index of what? They represent like
these two here?
Yes.
So,
like it doesn't matter. N1, N0.
So N1 is the index of the scatterer itself, and N0 is the index of the environment, the matrix around the scatterer. Okay?
So we assume that the scattering medium is inside a bigger medium?
Yes, right. Okay, so it can be free space, but it can be also physical matter. Okay. Okay, so you have here a calculator. So you all of you have computer or phone, so you can enter this website, and I let you do it. Can you? So it's https://omlc.org.calc.me me underscore here me underscore calc. Maybe it's on the Moodle or should be on the Moodle, yes. Actually, you can program that. This application, you can program that on the tablet.
I'm not sure if I understood correctly. So S is dependent only on T and phi, and this is the probability diagram of which direction will the particle scattered after scattering.
There's no particle in that case. It is light.
Okay, so yes. But this is like a probability function of the electric field direction after it. So the highest probability is like no scattering at all, like 0.
No, the highest. I mean, no, that's in the 0 direction, in the direction of incidence.
So I have like a higher probability that I won't see any change. Like if the photon come with 0, so it will continue with 0.
So the wave comes from here, okay, and you see that maximum probability is here.
So yeah, there is the highest chance is that I won't see anything, like no scattering.
No, but actually this is scattering. You can scatter, but in the forward direction.
And you can see the difference with or without?
What is it?
Like, can we see the difference if a particle did not scattered, or is scattered but didn't change its direction or angle, something like that?
Yes.
The amplitude maybe can change a little, but
so you have two components. You have a wave that propagates like that. Okay. Part of it will continue, okay, and part of it is scattered.
Oh,
so this is
okay.
the part of the light which is scattered. Which is scattered in different directions.
So
And
if
it
I
can be-
integrate all the graphs, so I get the energy that I had before.
if you integrate that, that's what we are going to do that, by the way. If you integrate that, you get the part of the light that is not propagating anymore in that direction,
Okay.
which has not been, with everything which has been scattered, which has been lost. Okay.
Okay.
Although this part here is re-injected in the same direction.
Okay.
Okay.
So it's like a density graph that shows the field after the scattering line. Like you have most of the field like continue without like in the same direction, but you have some that scatters either backward or.
Exactly.
Okay. Okay.
I will repeat that. I mean, it's very important to clarify this diagram.
But like, let's say, in the macro scale, if I shoot a photon and it's scattered, so it's not like that. You can see where the photon went. Like Rutherford scattering experiment.
What experiment?
Rutherford when
Rutherford,
yes. So the scattering there, it's like
That's all particle, right? You look at particles. So it depends if you look at particles or if you look at waves. Okay, you can see the particle as a wave, and you see that the physics is very different.
but if I
In terms of probability, I mean, it's the same as talking in terms of probability of particles. Okay, looking at the Schrödinger equation. Okay, the probability of presence of a particle is for us the intensity of light. The intensity of light is the probability of presence of the photon.
So you can look, like, I don't know, maybe Michelson, when you have like gamma radiation, you see like scattering, but after that you can measure the angle, like you can see where it goes. So here it's like, yes, you can have a lot of direction for the field, but eventually the photon go to a specific direction.
So in that case, for instance, most of the photon will go forward,
Ah, okay.
will be scattered forward. Right.
Okay.
Look at that as a probability distribution.
But if I like shoot like, I don't know, like 1 trillion photons, so I should see some get backwards
Yes.
from this diagram. Okay, yes.
Okay.
Yeah.
So this is it also. Yeah.
דיברנו על התעסקות בפרופלו בעיקר. לא יודע מי זאת, אבל ראית באמת תסכים ואיך היא נראית. אבל זה לא רלוונטי, אחי, זה רק נורא, כאילו זה ג'וס נחמד, אבל...
זה צהוב, אחי.
בסדר, אבל זה מה שמעצבן אותי בתקשורת.
זה צהוב, מה אתה רוצה?
אני מושך לייק.
So let me just explain maybe more specifically what happens here. Okay, what we are looking at here. So the zero here means the direction of incidence. Okay, so we have a plane wave coming from here. Okay, coming from this side here, being scattered by the scatterer. Okay, and the plane wave continues. Okay, what we are looking here at is the part of this incident wave that has been scattered, that has been lost from the initial plane wave. Okay, so part of the wave will be lost, and will be lost in all those directions of scattering. Okay, so see that as a probability distribution with angle of the possibility to find the light in all those directions. Okay. And it can be also in the forward direction. You can have part of the light which is scattered in the forward direction. Okay. You may ask how, but you don't ask.
How what?
We'll see actually. We'll see how it can happen. Okay. But yeah, you have to think. Yeah, I try to push you. See that to think in terms of waves, not in terms of particles. Okay. So if you want to go from particles to wave, you have to think about in terms of probability distribution, for instance. Okay. And this is in the far field. Don't forget that what we show here. So I don't like this picture here because it seems to be like around the scatterer, but this is actually very far from the scatterer. Okay, so that was the physics for the simple case of scalar waves. Okay. What about if we move now to vectorial waves? So a little more complicated case, not so complicated, but just to give you the example. So for sound waves, instead of waves in air, it would be elastic wave propagating in some solid. Okay, so in that case you can see that you have different polarization, different ways for the wave to propagate in the system. So it can be pressure waves like that, it can be S waves, okay, it can be shear waves like that. I mean, all those are different solution of the wave equation in this particular system. Okay, for sound. For electromagnetic waves, it's quite more simple. Okay, why? Because we have so what we have is an electric field and a magnetic field that oscillate in time and position. Okay, principle they are orthogonal. The E field and the B field are orthogonal with each other. Okay, and the direction, let's say, of the E field here defines the polarization of the wave. Okay. So in that case, we have a linearly polarized wave in that direction. Okay. I don't know why I put this picture. That's not the point here. Okay, so let's see how we can formalize this question. So again, we have the incident wave, the incident electric field here, which is described by an amplitude here. So this is now a vector, okay, which describes the polarization. Also, it has an amplitude and the direction of polarization.
E0 is the vector.
E0, yes, the E0 gives you both the amplitude and also the direction of polarization. Here, E0 times small e is the unit vector for the polarization. E0 is a unitary vector which describes polarization of the incident wave. For instance, linear polarization. That's this example here. So here you have the electric field oscillating in that plane with the direction given by E0. Okay, so let's do it again. So we have as our scattering center here, we have an incident field. Okay, this incident field has also a polarization E0 relative to the plane here that's the angle. It's given by the angle alpha here. Okay. So the wave propagates, hit the scatterer. Okay, and in the far field again, looking in the far field, you will have a scattering field in some given direction with some given amplitude, and also with some given polarization. Okay, so the polarization can turn from E0 to ES here. You can have a rotation of polarization due to the nature of the scatterer itself. Okay, in a particular direction, theta and phi. In a different direction, it can be a different polarization. So that's a more complex function. Okay, actually, it's not a function anymore. This is like a tensor. Okay, so the field, the scattered field, is the incident field. Again, we still have a spherical wave away from the scattering center, okay, and a tensor here, a matrix here, S of u, which is a 2 by 2 matrix, okay, complex matrix 2 by 2 for a given direction u, theta, and phi. Okay, so for one direction, you have a 2 by 2 scattering matrix. So this matrix is given here. So let's define a basis for the polarization. Okay. So the plane of reference will be the scattering plane. So that this is typically the plane of the board here. Okay. So we look at the wave coming and being scattered in the theta direction here. So in that plane, you can define. You can decompose actually the field in two components. The one which is parallel to the scattering plane, okay, so on the board, parallel to the board, and perpendicular to the scattering plane, okay, so E parallel and E perpendicular here. So this matrix actually tells you how you mix the different components of the incident wave, parallel and perpendicular, how they are mixed together to create a new state of polarization for the scattered wave in the particular direction that we are considering, okay? Times the spherical wave, okay? So now it's not only one number, but it's 4 numbers. So each component of S depends on theta and phi, on the characteristic of the particle, the shape, size, composition, and the frequency, okay? Here it's supposed to be animated. That was just an animation to show you what is linear and so we have different type of polarization. So linear polarization, circular polarization, elliptical polarization here. How do you go from this to that one?
You can make like a phase difference between the electrical and magnetic fields. So
no, just the
just with the electric.
The two components. Okay, there is a parallel and perpendicular component.
So you make like
if they are in phase, what happens? If they oscillate in phase, what do you get?
So I get like a difference like the total vector of both of them will be changing.
But what would be the direction? What would be the polarization if they oscillate in phase?
In phase, so it will be linear. If they don't phase in the same time, so it will be circular.
So if they are in quadrature, okay, like a sine function and cosine function, okay, we get circular polarization, counterclockwise or clockwise, depending on the sign. And if it's arbitrary phases, okay, then you can have this kind of polarization, okay. So I put here exercise, find the relation between E parallel, E orthogonal, and so that this one basis for polarization. You can use another basis, which is the basis of circular polarization, which is either right circular or left circular, okay, depending on the direction of rotation. So this is another basis. You can go from one basis to the other, okay, and circular polarized wave is one where the electric field has constant magnitude, but its direction rotates with time. Okay, good, like here. Okay. So if you write it like that, E of t is E0 cosine omega t E parallel plus E0 sine omega t E orthogonal. Okay. So the phase is actually here between the cosine and the sine wave. Okay. So if you remove the time here, if you take the time out of this equation, okay, what you get is a simple relation for the right circular polarization left polarization, which is E parallel plus I. This is the phase. This is the quadrature here. E orthogonal. If you normalize by, can you normalize by square root of 2, and here is that. Okay. Very simple exercise. Okay, so just to tell you that. So by the way, do you know what is the difference between a tensor and a matrix?
Between what?
A tensor and a matrix.
Tensor has like a physical meaning. Like a matrix can describe, like, I don't know, even something in financial things, not specific like physical meaning.
Okay.
Like in tensor you can do all kinds of like tensoric math. You can, I don't know.
So that's the idea, but simply say it here in that case, for instance, okay, S is a tensor. That means that the tensor means whatever the basis I'm using, parallel, orthogonal, or circular, okay, this is the tensor S, okay, the amplitude, the scattering amplitude, okay. Now when I write it, I write a matrix that can be different if you use one system of one basis or another basis. So,
and tensor doesn't change.
The tensor is the same tensor. The matrix can be different. Okay, that's the way you write it. Okay. Okay. I was looking for that in ChatGPT to explain it. It's well explained there, very simply. And it's always something that bothered me. It's clear. He said that it's like a melody. Okay. So a melody is the tensor. But the way you write it on the paper with the note, you can take a system on another system. That's the matrix. I think it's a nice illustration. Okay, so just to finish this part, special cases. So in principle, it can be quite heavy computation. Computation of the scattering coefficient requires the full calculation of the scattering problem for Maxwell equation. Okay, so that's actually what is done in this small program. The case, the simple case, is the case of a homogeneous spherical particle. Okay, the fact that the particle is spherical, that gives you S2 and S3 equal to 0, which means what? If S2 and S3 are 0, so you have only the diagonal terms in the matrix. Okay, which means that you don't change the polarization. The polarization is preserved, right? So that's a good case. The case of spherical particle, the polarization is maintained by the scattering. Okay. Case of the forward scattering. So that's when most of the energy is scattered forward. In that case, okay, S1 is equal to S4. Equal to S. So that's the diagonal term actually is just one. So actually you go back to the case of a scalar problem. Okay, good. Let's move to the next part of this course. So let's talk about cross sections. Okay. Until now we have discussed this concept of scattering amplitude, scattering intensity. Okay, which is a little complex to understand, to realize, and we show with this diagram, scattering diagram, how the field the scattered part of the field is distributed. But let's move to something maybe more useful, a quantity which is more useful, which is the cross section, the concept of cross section. So this is just an illustration, okay? If I want to give a general definition of a cross section, the cross section is a measure of the interaction between the wave or particles with the target. Okay, that's the cross section. So you have particles hitting a target, for instance, or you have a wave going on a scatterer. Okay, to measure this interaction, actually you want to measure the part of the energy that is taken from the incident wave. Okay, this, if you can measure this part, that will be the cross section of your scatterer. Okay, so there is two types of cross section. So that's the title here. You have the geometric cross section and the scattering cross section. What is the geometric cross section? That's a purely geometric quantity. Okay, so you have, let's say you have a sphere. The wave comes onto this sphere. Okay, what it sees is a screen. In fact, okay, it's a screen which is a disk. Okay, given by the section of the scatterer itself. Okay, so that's really the geometric cross section. It's just a geometrical problem. Okay, like particles just hitting a target. Okay, so if the energy of incident wave is blocked by this object, this surface here is the cross section, the geometric cross section of this object. Okay, but when you consider waves, the story can be very different. Okay, and actually the cross section of this object, when you consider waves, that means waves can interfere, they can diffract, they can be in resonance with the object. Okay, so there is a strong interaction between the light, the wave, and the object itself. Okay, then you can have something completely different, and you can even have a scattering cross section which is bigger than the geometric cross section. Okay, so that's the big surprise in that case. You can actually have something very, very different. Okay. So that's what I wanted to say. So just to give you maybe an intuitive image. Okay, if you consider, for instance, if you consider an antenna, okay, an antenna can be very small, but can have a cross section which is very large. Okay, why? Because you can have a wave that comes in resonance with this antenna. Okay, so actually even an atom, as small as it can be, if its transitions are in resonance with the incident wave, okay, then it can have a cross section which is much larger than its size. Okay, much larger than its size. Okay. So the radiation can be stronger than the simple area occupied by the object. Okay. So let's see. So let's define this scattering cross-section. First, very important, the scattering cross-section is homogeneous to a surface. Okay. Okay. So in the simple case of the geometric cross-section, that's the surface of the section of the scatterer, which is seen by the light. Okay. In the case of scattering cross-section, so how do we define it? So actually, you can see it here. Okay. The scattering cross-section is the ratio of the energy scattered over the incident intensity. Simply
is the
saying.
power?
So P is the power. So the incident power or the incident intensity on the surface, okay, on this surface, sigma S, is exactly equal to the scattered energy in all directions. Okay, so you look for the surface that will block geometrically the same amount of energy that is scattered in all directions by the scatterer. No, not clear.
I don't understand what is the power. of this.
Or power intensity, okay, it's the same, okay. So you have an incident wave, okay.
The power that is used in the scattering.
So the power of the incident of this incident wave, okay, when it meets the scatterer, part will be scattered in all directions. So it is lost for the direct wave, okay. This part which is lost, okay, compared to the incident intensity, gives you a surface which is the scattering cross section, okay. So yes, so the units here of the intensity is watt per meter. This is watt per meter, and you will square. This is meter square. Okay. So that's the definition for the scattering cross section. Scattering. Okay. So how do we calculate that based on what we learned before? So always take a system in the far field. R goes to infinity. You just integrate over a sphere of radius r the intensity, the scattered intensity, Is. Okay. That's the power which is scattered. Okay. The power which is scattered, which is the incident intensity times sigma s, is equal to the scattered intensity here over through a given element surface. And then you integrate to all the space, the space, the 4p solid angle. Okay. So if you write it in terms of solid angle, ds is r squared d omega, where d omega is the solid angle, okay, which is sinus theta, sine theta, d theta, d phi, okay, and Is, that was what we presented at the beginning. Is Su, okay, the amplitude, the scattering amplitude modulus square over the distance r square times the incident intensity.
What is sigma s?
What is this?
Sigma.
No.
The first line.
So that's what we want to calculate. But by definition, this is the scattering cross section. Okay, so I just go back here. Here, the scattered power, the power which is scattered by the object, okay, is equal to the incident intensity times this surface, okay, or in other words, this surface, the ratio between P scattered over incident intensity, okay. So I calculate this part here, okay. So this part is here, okay. I replace I integrate actually the radiated intensity in all directions, theta phi at the distance r, which I take as large as possible, okay. But just for calculation, I take it finite, okay. So I just replace ds by r2 d omega, where d omega is the solid angle, okay. So if you replace that, what you obtain is just by definition, so sigma s. So here the I incident just disappeared, it's on both sides, okay. So sigma s is the integral over all the solid angle, over all space of the solid angle of SU. So the amplitude, scattering amplitude, modulus square. So you take this diagram that we showed, okay, and you just integrate over all angles, all theta, and all phi, okay, and you get the scattering cross section. So this is just the integration of all the energy which is scattered everywhere, okay? And this is the surface.
And it's the cross section for all the scattering medium.
For what we are talking about one scatterer, okay.
One
So you take a scatterer and you say what is the scattering cross section of this object, okay. That means how much light is lost when a plane wave comes across this scatterer, okay? And if it was just geometric, okay, that will be the size of the scatterer, okay? But because of the wave nature of light, okay, that's what you calculate here, and you get a surface which can be different from the size of the scatterer itself, okay?
We assume that the whole area of the scattering scatter in same power?
No, no, no. It's an object. Okay. Let's say it's a sphere, for instance. Okay. So it's a sphere with a different index.
In our example, cloud in Eiffel Tower.
Right.
The cloud in the middle of the cloud, the scattering power is very big from the edge of the cloud.
Right. Yeah.
So
but yeah. For now, I'm considering only one particle. Okay. One droplet of water in the cloud. Okay. Okay. So this particle will take away part of the incident energy coming from the Eiffel Tower, okay, and is given by sigma s, by the scattering cross section, okay. This is what is lost in the propagation. Then there will be another one that will take part of it, and one after the other. Every scattering event will reduce the intensity of the incident light, okay, and then you get what you observe actually from the Eiffel Tower, okay. But that's a measure of the efficiency of the interaction between the light and the object. Okay, so that's actually the formula that we can write directly from what we learned before, from the expression of S of u. Okay. Okay, look at this picture. Okay, so that's for scattering. Okay, but you can define also the cross section for absorption. Okay. If the object absorbs light, okay, for instance, it has some color, okay, so it will absorb some wavelength, okay, so we can the same way define a scattering, an absorption cross section, okay, which is the ratio of the total power absorbed by the particle over the incident intensity of the wave, okay. So we can define that for scattering, for absorption. Okay, that's typically the two effects that can reduce the power of the incident light. Okay, and usually people consider both of them together. Okay, so we consider what is called the extension cross section. Extension means both scattering and absorption. Those are the two mechanisms that take away part of the energy, incident energy that in the interaction with the scatterer. Okay. So the power, the extension power is the incident intensity times the extension cross section. Okay, which is the total power taken from the incident wave, including the scattering and absorption. Okay. So this is very important, for instance, when you can consider scattering by tissues, okay, through the skin, through the tissues, because they don't only scatter, but they also absorb light, okay. So these two parameters are important, and especially to see which one dominates, okay. Is absorption stronger than scattering? That means that actually the energy will decay very fast because it is absorbed by the material, or it is because of scattering, okay? And those are two parameters that can be very useful for imaging, actually. I will describe that at the end of this course. Okay? So, just to summarize here, we have a plane wave incident on this object here, okay? This object has a geometric cross section, okay? This big sphere has a section here which is geometric cross section, okay? At the output, far from the object, okay? Part of the light is lost, okay? And it is illustrated by this area here, okay? Which is the scattering cross section, okay? So in that case, we have a geometrical cross section larger than the scattering cross section in this picture, okay? The ratio between the two is called the efficiency factor. So Q is sigma S, the scattering here, over the area, the geometrical area of the object. Okay, so that's the definition of the efficiency factor. So the efficiency factor is the scattering cross section relative to the geometric cross section. Q is sigma S over A. Okay. So this gives you the size of the scattering shadow relative to the geometric size of the particle. So for a spherical particle, for instance, Q will be sigma over pi R2. Okay, and this is general. I mean, you can define that for scattering, for absorption, or for in general for extinction. It's a dimensionless quantity. Okay, and interesting enough, it can be larger than 1. That means that the scattering cross-section can be larger than the geometrical cross-section. Okay, so that's really that's actually express the fact that there is an interaction between the light and this object. Okay, it's not simply a screen. I mean, the light penetrates the sphere. If it resonates with the sphere, energy will build up inside the sphere and will radiate after that in different direction. Okay, or if it is like a very small particle, like yeah, just a small particle compared to the wavelength. Also, you may have it may work like an antenna that radiates back the energy. All this can make the this Q factor, this efficiency factor, larger than 1. Okay, any question? Hi. So I would like to introduce you with a very important theorem. It's called the optical theorem or the extinction theorem, given by this formula here. So what do you see here? So sigma x means the extinction scattering cross-section, the extinction, sorry, cross-section, okay? Meaning
the extinction cross-section?
So again, the extinction includes both of the forward scattered field. Okay, so part of the field is scattered in all directions, part of it is scattered in the forward direction. Okay, now the scattering cross-section, I mean the amount of energy which is lost in the scattering is related to the light that goes directly forward, which is scattered forward. So it's very important to understand what these things mean. Okay, it tells you actually that to have scattered light, you need to have an interference between the incident wave and the wave that is scattered in the same direction. Okay, so imagine that they are in phase. Okay, so that will give you a scatter that will give you a lot of scattering in the forward direction. Imagine that they are out of phase. Actually, you will have almost nothing scattered forward. Everything will be scattered in another direction. Okay, so it's very interesting to see that as an interference effect. It's a wave effect. Okay, and the amount of energy which is lost from the incident wave, okay, result actually from the interference between the incident wave and the wave which is scattered in the forward direction. Okay, so it's really, you have to look at that really in terms of waves and interferences if you want to understand the effect of scattering. So you see the scattering effect is not anymore like a particle that hits an obstacle and goes in another direction. Okay, here it's an interference effect between the incident wave and the wave which is scattered in all directions. Okay. So the extinction process is not due simply to the blocking of the wave, geometrical obstacle to the wave. Okay, but it's an interference phenomenon between the incident wave and the wave which is scattered in the forward direction. Okay, that's only because only this one will interfere with the incident wave. Okay, they are in the same direction. Okay. So that tells you what actually? That tells you that this term here actually encapsulate all the information about the scatter. Okay, you don't need. In fact, you don't need to have S, the complete matrix. The scattering in the forward direction is enough to have all the information about the scatter itself. Okay, everything is encapsulated in the forward scattering. Okay, so here. So it reflects the fact that the very existence of scattering requires scattering in the forward direction in order to interfere with the incident wave and thereby reduce the probability current in this direction, the probability intensity in this direction. Okay? If you don't have S0 forward scattering, you cannot have actually you don't lose energy. Okay? Because there is no interference with the incident wave. So this means that the field scattered in the forward direction contains all the information on the scattering and absorption of the particle. So let's demonstrate that. Okay, let's demonstrate this theorem. We do it now.
We can take a break if you want.
Can we break?
Yeah, okay, we make a break and then we go to the demonstration.
Patrick, can you move backward like one slide? So here it's like the same when we learn like in quantum mechanics about reflection and transition, when reflection is the imaginary part of the function. So it's like the same. Here you just want to see what didn't transition to the same direction. So you said, oh,
the imaginary part is not what does not go directly in the forward direction.
No, in quantum mechanics, like the reflection, yes.
The imaginary part?
When, how do I say it? Like, when you have a wave function and you have like, I don't know, like a potential wall, and you want to measure or calculate the transition and the reflection.
Transmission and reflection.
Yes, so the reflection is the imaginary part of the wave function. So when you say about it,
I like to see what you mean.
Quick question, אחד לא היה.
We can go out for
רוצים לדרך של כאילו העברה והחזרה.
לא, אני מבינה, בתוך פרופ פוטנציאל, כן, הבנתי לך, אבל אני לא זוכרת שזה מיוצג על ידי imaginary part. אבל שמע עדיין לא עשיתי, אני עושה בקוונטים שלך.
אני לא יודע, לא למדתי פה תואר ראשון.
If you can find that.
כן.
By S of 0, do you mean like the diagonal that you showed before? S of 0. Is it like the diagonal that you showed before?
כן, אני שומעת חוויות קשות.
Yeah, only the elements of the diagonal.
אתה נהנה כאן בינתיים?
Each element depends on the direction that you consider. So you have the incident wave, okay, and then you look at the scattered light in all directions. So you have
מדהימה, למרות
theta,
שעכשיו הנה,
and
משהו
you have
לקונט,
okay.
לא יכולתי לגשת פיזית לשני מועדים.
Okay, so in that direction theta, you have some probability to have some scattering. Okay.
רציתי לגשת לשני
Now
מועדים,
theta equals 0, so that means the same direction as the incident wave.
כי אני רוצה
That's
לראות
the
מה...
S0 here.
סבבה שאני לא עושה תרגילים וכאלה, אבל אני רוצה ללמוד את הקורס בכל
I
זאת.
see, yeah.
אז אמרו לי, לא אי אפשר
You
לפתוח
missed
את
the first part.
למה? או שתוותר על ה... כאילו לגמרי, תירשם לקורס מחדש, תעשה את המטרות, תעשה הכל, נפתח לך את המודל, או שרק תיגש למבחנים ואין לך מודל. אני פשוט מבקש מאנשים עכשיו לשלוח לי כל פעם את התרגול.
רגע, שילמת כאילו בתל אביב על הקורס?
לא, פה זה בשביל תואר שני כאילו.
מה? מאוד מוזר.
דיברתי על זה כבר עם...
דיברת גם עם יוסי?
לא, עם יוסי כבר ויתרתי לדבר.
לא, לך ליוסי.
אני מעדיף לגשת לריטה.
ריטה מקסימה. יוסי, אני פשוט אוהבת לבכות אצלו, אז כאילו... אני יכולה לסיים מבחן, אני פשוט אוהב יוסי. מאוד מוזר לי, זה לא התנהגות שלהם.
That's the definition of the
כן, זה
scattering.
קונציפט שאתה מתאים לתל אביב.
So you have a plane wave coming
זה קצת בסה, קורסי
in
יהדות.
that direction.
כן, אבל לפחות הם עושים את זה בקטע, כאילו אין לי מאוד תחושה של הדתה
The
פשוט.
scattered
אז אתה
part,
רואה איזה קורס לוקחים,
the energy that is not continuing
דוחף לקורסים
straight
הפחות כאלה,
forward, okay?
ויותר מתוקשבים וכאלה.
כן, אבל לא, יוצא לי גם להיות
far
בפיזי.
from the scatter, in the
אבל נגיד שנה שעברה לקחתי קורס.
Okay, and what you observe actually is this function, this is just a spherical
והיו גם אתיופים בקורס.
times some probability here.
לא יודעת על מה
And the
אתה
probability is not
רואים
actual
בצורה
function. Okay?
סביר, אבל...
And u is theta phi, okay, it's just the direction. Okay, so for a given direction, you have more or less energy in that direction. Okay?
So this is the amplitude.
Yeah, so that gives you the amplitude.
The probability.
Yeah, amplitude for waves is like the probability for particles.
Yeah.
כאילו מעבדה נקראת המכון למולקות על ועל מגנטיות.
I see.
אנחנו עושים גם פרויקטים
And
שלא
then when you
קשורים
say
למולקות
0,
על.
that's 0 and phi 0, so it's just what's
Just
כן,
pointing
כן,
to the
מעבדה
direction.
חזקה בתחום.
So
עושים דברים די
It's
מגניבים.
the way.
זה מתחלק לשניים, כאילו יש את החלק של יוסי יותר, של שרון,
you can play with this
הוא לא
calculator here.
מכירה אותו.
So it shows you, for instance, in that case we have
כאילו, אני נגיד ממש מלפף סלילי
the
מוליכה.
particle with index 2, the rest is 1, okay? And x is the ratio between
כאילו, לכו לבניין ננו, תעשו תמונה, תבדקו על התכונות.
2PA, so the 2P arc, the circumference of the sphere, divided by lambda.
האמת שכבר אני ממשיך בתל אביב, הייתי אצלו כל שנה ג'
Yeah, so lambda is, so the size of the system is about 3 times the lambda, okay? So this is a kind of big scatterer, okay? So the light will really go inside, will interfere inside the system. And what you see is that, so in the forward direction,
באמת החלקה מקסימה, כאילו כואב
far
לשמוע
from the
שזה
scatterer,
שקע,
you
כי
have
אני
a high probability of
זה בקטנה, בסדר? כאילו אני מבקש ממישהו מהמעבדה שלי שגם עושה את הקורס, שלח לי כל פעם את הקורס.
כן, אבל
is
זה
small
אבל
probability
כאילו,
to be flat scattered or be scattered in other direction.
אפשר לקווה שזה פעם אחרונה.
לא, הם
So
עושים
these are the polar representation where you have, I mean, these factors are the intensity.
לא, אתה לא חייב לפתוח.
הוא לא משקיע.
So it's
בסדר,
when you go away
זה
from the
עדיין
center, you increase intensity. So there is high intensity here, low intensity here. Okay. And
גם
this is
כשעושה
theta.
קורסים והמרצה עושה מה
The
שבא
phi
לו,
angle is
הוא
this.
חורג מהנהלים ואז שאתה בא
This is
להתבונן,
only two dimensional, so it's
יש לך
just
מכתב חזרה כזה, נקרא מחזור, מישהו לא טוב לו שזה זה התשובה שלי.
מה הקיבול, מה הוא
The same
יכול
way, just rotate this way.
זה כאילו.
נגיד,
I see.
היה לנו שני מקרים קיצוניים,
This
So
is-
you must
מקרה
have
אחד
some energy
שהוא
which is,
כאילו קורס שהממוצע בו בדרך כלל היה כזה
forward.
80 בשנה, זה
and
קורס היחידי שהיה
this
סביר
part
כזה,
here
פתאום
will
במחזור
interfere
שלנו
with
הוא
the
ממוצע
incident
52.
wave.
טוב, כאילו
which
זה
continues,
בסדר,
okay?
אתה צריך לעשות פקטור לפי התקנון, אתה צריך להשוות את זה לחציון
This
של
will interfere
המחזור,
with the
להתקרב לחציון או משהו כזה.
and will give you
ואז הוא אמר,
actually
אני בהרצאה האחרונה
what is
לימדתי
lost
אתכם,
is lost in the
זה היה אז כאילו פונקציות גרין,
in the process of
זה
the
לא היה רלוונטי
This is
לזה,
one dimensional.
כן, אבל זה היה בממפיס
So
אחד,
you see how it comes.
הוא כאילו לימד את
You
זה
see how
כזה
it comes.
כאקסטרה, הרצאה האחרונה, וגם זה לא היה במבחן, זה כאילו לא
Is
עשו לו,
it
מי מלמד
something
קצת
that can
גן
be
ביום
described by
אחד?
סתם,
spectral
זרק את זה כדוגמה כאילו, ואז הוא אמר, כן, הנה סילבוס חדש, יש פונקציות גרין, אין חציונים של שנים קודמות, זה היה ככה. זה היה ככה.
just
והאוניברסיטה זרמה איתו.
looks like that.
למרות שזה לא היה במבחן, למרות שזה לא היה בסילבוס, למרות שזה לא היה בכלום, זה רק השאלה בשיעור האחרון, וזה זרם לו עם התירוץ ללמה הממוצע כזה נמוך. ואותו דבר לנו גם בקורס הראשון של סטטיסטיקה, הממוצע היה נמוך בפער משנים קודמות, בפער הוא כאילו ממש היה נעשה כאן במבחן.
זה אבל אצלנו זה גם למרות עכשיו חיפור מרצה.
כן, אין לי בהם קורסים קשים, פשוט לנו קורסים שהממוצע כל שנה הוא 50, ואז אם תקבל כאילו הממוצע 50 זה סבבה, אין בעיה. הבעיה עם קורסים
אחת
שבדרך
אנחנו
כלל
יודעים מה זה תואר שני, זה הממוצע.
כמעט לא מתקבלים. יש אצלנו קורס פיזיקה סטטיסטית, עשו על המרצה שלנו כתבה בכלכליסט, ואז הם שינו את התקנון אחרי זה, זה הכי מצחיק בעולם. הקורס הזה, כאילו עד איזה 2022, היה ממוצע 19, כאילו זה היה הממוצע, ואז עשו עליו כתבה בכלכליסט, זה אחד הממוצעים הנמוכים בארץ וזה, ואז שנה לאחר מכן, גם רואים את זה בסריקות של המבחנים שנים קודמות, הוא הוסיף כזה הערה בטופס, כל מי שמקבל מתחת ל-50, מקבל פשוט ציון 50, ואז הממוצע קפץ להיות 50, 51. ואת מבינה, כאילו, במקום לעשות איזשהו תיקון עם עצמך, הם כאילו, זה הפתרונות שלהם לדבר.
לא, אז כאן... תשמע, כאן, לפי מה שאני הבנתי הרמה בקורסים, כאילו בהרצאות זה גבוהה, גם שיעורי בית, אבל מבחנים יותר.
כן.
אני חושבת שזה שילוב נכון, כי הם לא באמת מחסירים מבחינת החומר וגם לא הרמה ואופן החשיבה והדרך שבה הרצאות מועברות, כי גם יצא לי כאילו לצפות בהרצאות כזה במקומות נוספים, אבל אני מודה, אבל המבחנים באמת כאילו...
כן, כן. Patrick, this is what I meant. It's not like directly the imaginary part, but it's like when you have a wave function and you have the part that's before the wall and after the wall, like the potential wall or something like that. So this is the part of the reflection because you calculate it by that. So
לא, אבל זה לא מה שהתכוונת אליו, זה ברור.
So this is what I meant. I'm sorry. Because
לא, אבל you said imaginary part, אין כאן עניין של חלוקה, like distribution between
it's not like
real or the
all of it
imaginary
is like imaginary part, yes, but I meant like
It's just a complex number.
Yes.
yeah,
You have k plus k minus k. So one wave goes one direction and one in the other direction. So you have a standing wave between the two
yes.
walls.
Yes.
But in this part, it's like it's remind me this because I have one part that just gets through and one part that gets reflected, and you just looked at the one that gets reflected, and you said, "Oh, okay, this is the power that I lost. This is the cross section."
I think it's more like imaginary parts. It's like
So here it's not imaginary part, but it's like the
It means like there are still waves or light that come through these particles that has the same k, like the same wavelength,
no, they all have the same wavelength.
but the one that like
The same direction.
disappears, like the energy is in the particle stays, like the energy, or it comes out, like it preserves the quantity, right?
Yeah,
The energy, and where does it go?
Where does it go?
Yeah, like to the particles, or there are some other waves in other
No,
directions.
we are far from the particle. The particle doesn't keep the energy. It can stop for a while and then release the energy. But we are far away. Everything is released. Okay, so the particle is passive, and the energy is conserved. Part is the incident wave that continues, and part is the scattered wave which is scattered.
Yes.
Except if you have absorption. If you have absorption, part of the energy is lost. So if I go back to this diagram here,
the imaginary part in this diagram it's the left part of the diagram. Like if you move one slide, like the next slide, the log scale, yes.
it's the same as the log scale.
So the imaginary part is like the left side of the diagram.
No, remove that from your.
Okay, so that's where
This is the amplitude. Okay, we are considering the amplitude, but this amplitude has a real part and an imaginary part. Okay, it's a complex number. Okay.
Okay. No.
By the way, it would be nice to plot the real and imaginary part.
Okay.
We should do that.
I
That
think
could be
everything
great,
is represented by like.
Yes, of course, but I like. What I want to ask is like
You see in the demonstration, you will see where the imaginary part comes from.
But if you move to the log scale, so I feel like if you draw the imaginary part on the same thing, so it's gonna be really small here and really large in this part, no?
That's,
Not-
I don't know.
not a-
Maybe yes. I don't know. I have no idea. I don't know.
Okay.
I don't know.
Because you said that the power that we lost, it's
No,
the
but-
imaginary part,
but
and
it-
here it's there is no power loss in this direction. So I feel like it will be.
No, so that's what I wanted to re-explain here. She left. Okay. So what I wanted to say here, this is a scattering diagram. Okay, this is the part of the light which is scattered in one direction with some different probabilities. Okay, and you have the incident wave. So the incident wave interfere with this wave here, which is scattered. Okay, beyond the scatterer. So you have an interference between the incident wave and that part here, okay? And it's only because you have this part here, so it should not be zero. Because of this part here, you have an interference which can be constructive, destructive, whatever. At the end, you lose energy because of this interference.
Okay.
Okay?
So, okay.
So if the interference is completely destructive,
So this diagram is fixed. It's only depend on the part that you scattered with.
Right. But it
Okay.
will interfere with the incident wave, and the net result will give you how much is lost. But it's not lost. I mean, it's just because of destructive interference.
Yes,
Okay.
yes.
That's all the magic of waves or wave function for quantum mechanics. But you'll see in the demonstration where it comes from. So it's getting late, otherwise I will ask you to demonstrate it. Okay, so the optical theorem or extension theorem, very important theorem. Demonstration.
Look forward.
So we are going to write it exactly this way, okay? She didn't leave.
No, she's here, but I don't know where she's.
Okay, so we are the demonstration will exactly write what I just described, which is the interference between the incident wave and the wave which is scattered. Okay, so in the incident direction, in the zero direction, forward direction, the incident wave interferes with the scattered spherical wave. Okay, so let's write it. So the total field in that direction is this is the plane wave, exponential ikz. Z is the direction, okay, along the theta equals 0 direction. Okay, so that's the incident wave crossing on the other side of the scatterer. Okay, and this is the scattered part in the direction theta equals 0, phi equals 0. Okay, so S exponential ikr over kr. Okay, the spherical wave. So we just write this sum. That's the interference. Okay, field plus field will interfere. So in the far field, we can make the following approximation. Okay, if I want to write R is square root of x squared plus y squared plus z squared. You can assume that z is much larger than x and y. Okay, we are far from the scatterer, and we are looking close. I mean, around that direction, theta equals 0. So you can make an expansion here. You can take z out of the square root here and make this expansion, and you get z plus x squared plus y squared over 2z. That's okay? Okay for you? Okay, so if we do that, then I can re-express this. So this is an interference, okay, between two fields. So I'm going to take the modulus square of u. Okay, so if I take the modulus square of u here, u squared, so I will have the square of this term. So this is 1. The modulus square of this term is 1. Plus the next term in the expansion. The next term in the expansion is the double product here. So twice the exponential here times this term here. Okay, so I just replace r can be replaced by z. Okay, we are far from the source and close to the axis z. So r is replaced by z. S0 exponential ikr. So ik times x squared plus z squared over 2z here. Where is this z gone? Ah, okay, times exponential ikz, okay, which goes away because of the modulus here. Okay. So why do I take the real part here? Oh yes, because this is the double product. Okay, so you get actually twice the real part of it. Okay. Now this expression here can be integrated over a small area A. Okay, that gives you, can you see here, so integration of u squared dA, okay, integrating over this small area A, so 1 gives you A, so dA is dx dy, okay, so A plus 2 real part of A0 over kz here, and then you have two integrals here, exponent 1 over x and 1 over y of ak x squared over 2z. So you have two identical integrals for x and y. Those integrals are well known. They give you actually a number which is square root of 2 pi z over ik, okay, for both terms here. So if you just put things together, there is an I term here, you see. This I term will give you actually, will transform the real part into an imaginary part. So at the end you end up with an extension which is, so you have the 4 pi here over k squared, and the real part of s, so the z disappears, the 4 pi, and the real part of s, because of the complex number I, becomes actually an imaginary part.
What about A?
So what we do with A is a small area, so just neglect it compared to this part here. Okay? Or actually you can write this is the scattered light in the forward direction in some angle of surface A. Okay, so you can just normalize it and get the no. I think you can just neglect it. It's small compared to the rest. You make it goes to 0. That's it. It doesn't appear here. It does not appear in this term. Yeah, you just make it goes to 0. Okay. So you see actually the imaginary part comes because of the complex number I in the denominator. Okay, that's okay. Demonstration is fine. Mostly, what is really important is to understand that. I mean, this is really the interference of two waves. Okay, we just take the square of it, as when you do interferences between two waves, and you take the Taylor expansion. You neglect the terms in R square. You will consider the far field. Okay. You can generalize the optical theorem for vectorial waves. Okay, so that this time, I mean, S is a tensor, so you have to multiply it by the direction of polarization. That's not very important. Okay, so from here, I will define some quantities that are important. The scattering differential cross-section. So, as I wrote here, the scattering by a particle can be strongly anisotropic. As we saw some example, it can be very strong in the forward direction, not in other directions. Okay. So, the scattering, the cross-section is an integrated value. Okay, but doesn't tell you about the details. The differential cross-section d sigma over d omega describes the scattering angular diagram in an elementary solid angle in direction u. So this is the modulus square of the scattering amplitude. That's not more than the modulus square of s. Okay. And the total, the cross-section itself is just the integral over all the solid angle of the differential cross-section. So I'm not saying something new here. I mean, this is just another way to call the scattering intensity here.
That's in case when the geometrical shape of the scattering medium is not spherical or quadratic.
No. Whatever the shape of the scatterer. Okay.
It can be any shape.
Any shape, yeah. But the scattering can be anisotropic. Most of the time it is anisotropic, like more in forward direction or backward, or okay. This is just a way to look at an elementary cross section, because I use it for the coming definition. Okay, so before. So from here I define a phase function, okay, which is the normalized differential cross section. So P of u is some given direction. Let's say this is the incident direction. Okay, u is another direction. Okay, so P of u, if you want, is just defined by d sigma over d omega, normalized by the total cross section sigma s. Okay, so that if you integrate P, you get 4 pi. Okay. So this is just a normalized differential cross section. Okay. And now I get to the quantity that I really want to define, which is this parameter G. So G is called the anisotropy parameter, which gives you the degree of anisotropy of the scattering by a particle. Okay. So G will tell you if you are strongly scattered in a forward direction, or if you are more like an isotropic kind of scattering, like the two examples that we saw in the program. Yes. Okay. So depending on this value, so what is G? What is the definition of G here? So 1 over pi. So you integrate over all 4 pi steradian. You integrate P. Okay, so the normalized differential cross section times, so u times u is simply the cosine theta. Okay, so this is cosine theta. So you multiply actually the scattering amplitude, if you want, times the cosine theta. Okay, so you give, so if theta equals 0, cosine is 1. If theta equals pi over 2 is 0. Okay, so you give more weight to the forward direction compared to the transverse direction. So that's the definition of the anisotropy parameter G, and it's very important for us. You'll see in the future. G is of practical interest when the phase function is a function of the cosine of the scattering angle theta. What that means? That means that if you have, so that's the case for a spherical particle, many anisotropic small particle randomly oriented. So for small particles, that means that the size of the particle is much smaller than lambda. G is typically 0, which means that the scattering is isotropic. Okay, you have light scattered in all directions. So we see this is called the Rayleigh scattering by a very small particle. That's what we tested the second calculation we did. It was like a cycle on the particle, okay? Very small particle. So in that case, the anisotropy is 0. Okay? For large particles, just the opposite. G can be close to 1. Okay? Backscattering particle that backscatter light, G will be negative. Okay? So why is this important? We'll see later. You remember in the Eiffel Tower, okay, we have the source, which is the light on the Eiffel Tower, and then we have the scattering by the fog, okay. At some level, you don't see anymore the light, the source itself. You see light, diffuse light, but you don't see the source itself. If the scattering is isotropic, like this is the case in the case of the Eiffel Tower, with small particles compared to the wavelength, okay, then very rapidly we will lose the origin, the source of the light. Okay, we won't see it anymore. Okay, but if the scattering is done by large particle and the scattering is strongly anisotropic, strongly in the forward direction, so it will take more scattering event before we lose the direction of the source. Okay, so we have a source emitting. It will be scattered, but mostly in the forward direction, forward. Okay, so it will take a longer distance before we lose the information about the source itself. Okay, so we'll see that this parameter will define a new mean free path, which is called the transport mean free path. That will be actually the mean free path to consider when you consider multiple scattering. So that is just to give you words. We'll see that in more details later. But I wanted really to introduce this parameter G and the nature of the scattering, if it is strongly anisotropic or the opposite, isotropic around the scattering. So, by the way, that's two examples. Okay, so that's the case of very small particle. So you see the size parameter is small particle. The scattering is the same in all directions. Okay, so that's the case of a very small particle. The case of a very large particle, the scattering is forward direction, so strongly anisotropic. G is close to 1 in that case.
It's not very intuitively like when you think about it, why like a large particle won't have like a larger like scattering graph or something like that.
Right.
It's like the opposite.
Yeah, you would expect that a large particle will actually scatter
Better.
more in all directions. Yeah.
Okay.
Yeah, but okay. So we are not talking now at what happened locally in the scatterer. Okay, we are in the far field after the energy left the scatterer. Okay, but the interaction inside the scatterer is very important. Okay, and what happened there is that you may have many resonances. Actually, the light can be trapped inside the scatterer. Okay, and you remember these lobes that we see in the log scale here on the side here. They correspond to multiple order of resonances inside the scatterer. Okay, and actually it's like in the Fabry-Perot. When you are at resonance, then you have more transmission through the Fabry-Perot. You will say, okay, no, if I'm at resonance, maybe I should have a stronger reflection. No, that's not true. You store energy inside the system, and the energy can escape again in transmission in forward direction. So that's the same idea here. If you have strong resonance, if you store a lot of energy inside the system, it will be re-emitted by the scatterer, okay, in the same direction as the incident direction.
Okay.
But in terms of cross section, yes, I mean you have a larger cross section. Okay, that's because you have strong scattering in the forward, so the imaginary part of S0 is large. Okay, so that will contribute a lot to the cross section.
But when you think about it, so I need to ignore the fact that it's big, like it is transparent, so it doesn't matter the fact that it's big, it doesn't block the field, but it can like storage energy and let it transfer forward, unlike a small particle.
It blocks energy, for sure it blocks energy. Because you have a forward component, okay, and because of the theorem that we saw, the cross section will be proportional to the imaginary part of this S0. Okay.
Okay.
So actually, this tells you that the cross section is large here because you have a large component in the forward direction. So I want to finish rapidly by exploring the case of polarized light and how polarized light is scattered. So we saw that the scattering amplitude is now a tensor or matrix here, okay, with 4 elements. Okay, so those are complex number fields. Okay. Practically, when you want to analyze the scattering for polarized light, practically what you measure is never amplitudes, never field. You measure intensity. In optics, it's much more easier to measure intensity than fields. Okay. So I just want to mention to you an approach which is well known to achieve this type of measurement in terms of intensities, and this is called the Stokes vectors. So I go fast, just that you hear these names in case you are
familiar.
yeah, you meet that in your future life. You know. So what are the Stokes vectors? So we start from an electric field which is polarized, different components along different direction of polarization, and instead of the 4 parameter of the S matrix, the S matrix, what use is these 4 components here, I, Q, U, and V. Okay, so what is I? I is just the intensity of the parallel field and the intensity of the plus the intensity of the orthogonal field. Okay. Q is the difference of the two. U is a mixture of the two here, and V, V is actually also a mixture with the minus term here and the I. Okay, so all these 4 parameters actually there are numbers, things that you can measure effectively. So I wrote here, if you write E parallel as an amplitude, a phase term, and in orthogonal as an amplitude and phase term, you can express the Stokes vectors associated with the electric field and show how they can be measured. Actually, you can measure them directly. Okay? And then from these measurements, then by taking combination of them, you can retrieve the different components. So I show you here. So I is, so if you replace, so I'm using this notation here. Okay, A parallel, that's the amplitude, the phase, amplitude and phase here. Okay, I pass the calculation, but if you do that, you can find that I is the sum of A parallel square plus A orthogonal square. Q is the difference. U is twice A parallel L orthogonal times the cosine of the difference of the phases. And V is the sine of the difference of the phases. Okay? Actually, those 4 parameters, they are not independent. I square is the sum of the 3 others. So there are actually only 3 which are independent. But all of them can be measured. Okay. So let's see the interpretation here. Stokes parameters can be deduced from intensity measurements only, although they contain information on the phase. Okay. So I, very easy. I is just simply the total intensity that you can measure directly with the detector. Q is the difference of intensity of the 2 polarization. Okay, so how do you do that? You use a polarized beam splitter. Okay, it looks like a cube like that. The light goes through. One polarization is transmitted, the other one is reflected or is deviated by the cube. Okay, so you can separate the 2 components, and from that you can calculate the Q, which is the difference between the 2 intensities. Okay, so that's possible to measure. The other one I don't remember. So U is the difference of intensity between components along E parallel plus E orthogonal and along E parallel minus E orthogonal. So you use a polarized beam splitter turned at 45 degrees. Okay? So then you can catch the sum and the difference of the 2 components. V is the difference of intensity between right-handed and left-handed circular polarization. That's more complicated. I mean, you need to transform actually the beam into a circular polarization. So, but just with these 3 measurements, I mean, this one is not needed. With these 3 measurements, you get all the information on the amplitude and the phase of each component of the field. Okay, so actually you can retrieve all the information by using simply intensity measurement. Now, if you want to make direct phase measurement, the way to do that is to measure the interference between the scattered field and some reference. You need a reference field that interfere with your light to be able to transform it, to get the phase and the amplitude. This is much more complicated. that's the polarizing beam splitter. You have light. Any incident beam will separate its polarization. One will be redirected in that, and the other one will be just transmitted. So once you measure these 4 parameters, IQ, U, and V, then you can define what is called the Muller matrix, okay, which is a linear relation between the scattered stock vectors from the initial incident stock vector. Okay, so you can write the basis for your incident field, and you get the scattered field on this basis, on this IQ UV basis. That gives you a matrix, okay, that you can easily measure. The idea is really to be able to measure directly those parameters. Okay, so this just to give you, I mean, so you have heard of those terms. So stock parameters and the Muller matrix. This is well known actually in engineering. People are using that a lot, and that's it. So if you have any question on that, otherwise, thank you.
Thank you.
Thank you.
Thank you very much.
I made the heavy part really short.
Is it uploaded to the
I will upload
Also, I found this one. I don't know how accurate it is, but
So what did you do here?
no, just found it on Google. Organization, real engineering. So as I saw, it's like the measuring part is much like smaller than the real part.